Assalamualaikum and good afternoon to fellow panelists and presenters. My name is Abdul Hadi bin Mahmud, a PhD student from UiTM Tapah. The title of my presentation today is Effect of Anodizing Parameters on the Fabrication of Anodic Aluminum Oxide Nanopores on Aluminum Wires. My research involved developing immunosensor to detect porcine serum albumin in raw meats. One of my objectives in my research was to fabricate anodic aluminum oxide in its wire form for that application. So today I would like to share some of my findings as I characterize the anodic aluminum oxide I fabricated. Introduction. AAO, which is short for anodic aluminum oxide, is a self-organized material. High density of arrayed nanopores form its honeycomb structure. The parallel nanopore dimensions such as inner and outer nanopore diameter, nanopore length, and thickness of barrier layer can be controlled by adjusting the parameter during the electrochemical anodization process. AAO membrane is a well-established research material. It is considered one of the cheap, versatile, and highly functional materials. The anodization of an AAO membrane is well established. It has long been commercialized and applied in numerous fields. Although it is very useful and easy to fabricate, a freestanding AAO membrane is brittle and hard to handle for certain applications that require sturdy materials. Furthermore, the planar AAO membrane only provide a one-dimensional active site for functionalization. With taking that fact into account, we feel that another form of AAO should be studied to offer alternate choice in fabrication AAO. So, we started to fabricating AAO in its wire form. AAO in a rod-like form provide better handling and sturdy structure. The rod-like structure also provide the AAO with a three-dimensional active site for a larger active surface area. However, there has not been much reported study of fabrication of AAO in its rod-like or wire form to the best of knowledge. In this context, the main objective of this study was to fabricate an AAO from aluminum wire and study the effect of two parameters, which is the anodization voltage and anodization time on the development of nanopore structure of AAO wire. Methodology. The schematic figure illustrated the aluminum wire segmentation and anodization cell setup. The high purity aluminum wire used in this work was 1 mm in diameter. The aluminum wire was first measured and cut at 10 cm in length. Then, the aluminum wire was segmented into 0.5 cm exposed region for anodization by inserting the wire into flexible polyethylene tube. Two-step anodization was carried in this experiment. The electrolyte used was 0.3 molar oxalic acid and kept at 5 degrees Celsius throughout the anodization process. To study the effect of voltage and times of anodization, we varied both of these parameters with 9 samples as stated on the table. Result and discussions. Here is the image of AAO wire. The AAO wire was segmented for 0.5 cm each, so only exposed area is anodized. The wire was cut into individual pieces for easily handling and analysis. These are the SEM image of AAO with different anodization voltage, 40 volt, 80 volt, and 100 volt. From the image, it is appear that higher voltage result in larger pore size, but the pore distribution and homogeneity are affected with the higher anodization voltage was set. Looking at the relative standard deviation value, the higher the voltage, the RSD value is also higher with wider error bar. This is to show that lower voltage produce more homogeneous pore size throughout the whole surface compared to higher voltage. The structure of pore on lower voltage also more rounded and uniform compared to higher voltage. These are SEM image of AAO wire anodized at 40 watt with different anodization time. The first was 1 hour. The second was at 10 hours, and lastly at 20 hours. Longer anodization time resulted in larger pore development and change in the nanopore structure. The honeycomb structure can also be seen forming. Also, it seems that the longer the anodization time, it is actually increased the uniformity of the nanopore size and structure. Here is the SEM image of AAO wire anodized at active mode with different anodization time. The AAO was anodized at 1 hour, 6 hour, and 9 hours. Same result can be seen for AAO wire anodized at active mode. The longer anodization time produced larger pore and more uniform pore structure and size compared to less anodization times. This is the SEM image for AAO wire anodized at 100 volt with different time. The anodization time was varied at 1 hour, 2 hour, and 3 hour. The same pattern of pore versus time can be seen here. The longer the time, the larger the pore size. However, for the uniformity of size and structure, for AAO anodized at 100 volt, the pore started to vary in size more if we compare to lower voltage. And if longer anodization time was allowed, the pore size become less homogeneous. This might be due to the higher pore growth resulting from higher voltage and current. Conclusions. We were able to fabricate AAO in its wire form, and detailed analysis on the morphology using SEM revealed that pore arrangement and size depend on the voltage applied and time of anodization. Higher voltage result in higher current and lead to faster pore growth, but it compromises the pore arrangement structure and the uniformity of the pore structure and size. Time of anodization affect directly with the pore size. As the longer time took for the anodization, the larger the pore size developed. But longer time also helped to improve the uniformity of structure and size in the case of anodization under 40 volt and active mode. For 100 volt of applied voltage, when the time of anodization exceeds 2 hours, the pore structure started to be less uniform in size and structure. This finding will help to determine the parameters to choose for fabricating of AAO in its wire form depending on the application of the user. Here is some of the references in this work. That's all from me. Thank you.